Hello and welcome. My name is Bhuvan Unhelkar and I am presenting to you perhaps the most interesting and the most important module, which is starting with the basics of designing a class. Now, for all practical purposes, a class is a program. In theory, of course, it differs. For example, a web page may not be always easily modeled as a class, or a COBOL or a C program, which is a procedural program, may not have the opportunity for encapsulation or inheritance, which are one of those fundamentals that we had studied at the start. But still, a class can be roughly equated to a program. So for a good program design, we have reached now a stage where we are going to design classes and we are going to show their relationships. That is what we try and do in the basics of a class design. Now, until now, we worked in the problem space, we quizzed our stakeholders, we documented their requirements in a use case, we documented how the users will interact with the system, we created flowcharts, process maps, and we start identifying the classes. So for most purposes, a class is a common noun appearing either in the problem statement or in the use case description or in our interactions with the users. For example, in a banking domain, an account and a customer are the most fundamental basic classes that will come out of a use case description or a interaction with our users or a problem statement. You can find classes everywhere, but when someone gives you an example, right, this is how a particular customer withdraws cash in this bank, they are describing a scenario which is made up of objects. So our job is to convert or abstract those objects, those individual objects, and identify classes. Classes are made up of 3 plus 1, 4 parts. The name of the class, singular common noun, a customer, an account, a passenger, a patient, a doctor. All these are representing singular common nouns. That's the way you typically represent a class. You might have variations depending on languages, depending on the environment that is provided to you. If you are inheriting classes from a Java library, then those naming conventions will come into play. You then have a suite of attributes. And since a class can be mapped to a program, an entire system can be a class. But that will defeat the purpose of object-oriented design. So we take some potential classes, common nouns, who don't have their own behavior associated with them, and we put them as attributes in our class. For example, you have an account class, then you have its attributes like an account identifier, like the date account was opened, like the amount, the balance, the dates of transactions, whatever it is. You add all of these nouns as attributes to your class. And remember, it's an iterative process, it's an agile process, the process we are following to create a great system design. That means sometimes as you progress through the design, some attributes will become classes on their own, and some classes which you thought are independent classes may as well become attributes of another class. Then you will typecast your attributes. So you have a date attribute of type date. You have a amount or a balance attribute of type currency. So depending again on the language in which you are eventually going to code, the types that are provided by the language can be used in typecasting your attributes. And sometimes you will have user defined classes as attribute types. We will discuss further in the next chapter how to go in greater detail in designing attributes. Then you have functions or methods or operations, which are all the behavior of your class. And remember, we will not do data hiding, we will do encapsulation. That means we will design functions or operations in such a way that they encapsulate attributes in a meaningful manner. Now, attributes and operations can be both private and public, which is called visibility of our attributes and operations. A minus in front of an attribute represents private attribute, which is how by default we will define our attributes. And operations by default will be public, so that other classes in our system can access the data of this particular class that we are designing through the operations. And then up on top of the first figure you will see stereotype. So most business classes are stereotyped as entity. And then there are other types of classes which we will discuss later in this discussion or in this module. Now, once we have defined a class and we will have defined a series of classes, then we will try and show relationships between these classes. And although in the class diagram example that I have shown, there are three relationships. Basically, there are two. One is inheritance. A savings account is an account, or a checking account is an account, and the other is association, which is customer associates with an account, or an account associates with a customer. An aggregation, which is a collection relationship, is where an association becomes a specialized type of association. And then as you progress up, keep on abstracting higher and higher, you are generalizing. And if you are inheriting and bringing your inheritance hierarchy down, you are specializing. And the practical advice is be very, very careful. Don't go overboard. Sometimes in a .NET environment or even in a Java environment, you will find that the environment itself has a suite of inheritance hierarchies already. So from a designer's perspective, 3 deep hierarchy is quite a bit. So be careful in how deep you go, because then you have the question of granularity, that is how big or small the size of your class should be, and maintaining that inheritance hierarchy. You will then also provide more annotations on your class diagram, such as which class uses which other class, but not in the reverse. So it's a directional association. You will provide multiplicity on your class diagram. And a multiplicity is one instance of one class. That means one single object, say customer in a banking domain, will associate with how many objects of the other class, and this is the association relationship. So when a customer associates with account, one instance of customer can have no account, can have one account, two, or say maximum of three. Then the multiplicity on the account side will be 0 dot dot 3 or 0 to 3. If you look at the same relationship from an account side, an account must have a customer and can have at the most two customers, joint account as an example. Then from the account's viewpoint, the customer side of the association relationship will have 1 dot dot 2 to indicate minimum one customer, maximum two. You can always design a program saying initially we don't care, unknown number of customers. Then it is either a star or n. So those are the variations in terms of multiplicities. If you have a relationship between customer and account that is many to many, you move into what is called an association class or a link table if you are familiar with entity relationship diagrams, relational database modeling, where a many to many relationship can be simplified by adding additional table which simply contains the keys, primary keys of both these associated tables. So to an extent, awareness of ER modeling can help. The major difference of course is that in a ER diagram we don't deal with operations or methods or functions or any kind of behavior, but here we do. So that is the basic of a class design. I have given you some examples from hospital management system in terms of class diagrams. Those are also not enough to treat it as a final codable design. So in the advanced design discussion next module, we will look at how the whole design can be converted into a real life code. Until then, of course, we are experimenting with pseudocode. So I hope this introduction has been of value to you. Now you need to go through the chapter, understand the concepts, study the designs, ask me questions, do your exercises, and consolidate what you have learned. Remember, this is a major diagram, a major UML modeling construct in the solution space. So this becomes the starting point for the model of solution space. Okay, take care and good luck. Bye bye.